Okay, in this segment we're going to be talking about some basic quantities that we will be making use of and thinking about all semester long. And our first one is going to be charge. So charge we denote by Q, and the units of charge in the SI system are the coulomb, denoted by C. Now a coulomb is a fair amount of charge. 1 coulomb is the charge on about 6.25 times 10 to the 18th electrons. And 1 elementary charge, which is the magnitude of the charge on an electron, or a proton, would be 1.602 times 10 to the minus 19 coulombs. Now with each of these quantities there's going to be an associated preposition. And the preposition associated with charge is going to be on. So we talk about the amount of charge on the top plate on some capacitor, or the amount of charge on a conducting sphere, or the amount of charge on some node in the circuit. That's going to be our first quantity. Our second one is voltage, which is denoted by the variable V. The units of voltage are volts, which are also denoted by V. And 1 volt in more fundamental SI units would be 1 joule per coulomb. And so this is a normalized potential energy. It's sort of like gravitational potential, where we have gravitational potential energy and we normalize out the mass. And so we talk about mg being the gravitational potential. And in a similar way, the electrostatic potential, or the voltage between 2 points, is the amount of work that it takes to move a unit amount of charge from point A to point B. And the preposition associated with voltage will be across. So the voltage across some element in the circuit, or sometimes maybe between 2 points. Occasionally we will also have an understood or implicit reference point in our circuit, like ground, and then in that particular point, from that particular standpoint, we might also use on. We might say the voltage on a node in the circuit. But there's, in that case, always an implicit reference that we're bringing in, so that the voltage is defined between 2 points or across the circuit from one point to another. So you always have 2 leads that you use to measure voltage, a positive lead and a negative lead. And if the negative lead is always attached to, let's say, some conventional reference point, like ground, that's taken to be the sort of 0 point of potential, then we can talk about the voltage on a node or something like that. But please be aware that saying something like the voltage through a component is just not coherent. Okay, so our third quantity is current, which is denoted by I. Of course, I stands for current. Unfortunately, there are just so many letters in the alphabet, and C denotes lots of other things, as it turns out, like capacitance and coulombs and other things. So instead we, by convention, have come away with current being denoted by the letter I. And the units of current are the amps, or ampere. The unit of current is the ampere, or amps, sometimes abbreviated amps, which is denoted by A. And 1 amp is 1 coulomb per second. So current is basically a rate of flow of charge. So sometimes we will write I equals dq dt, and the preposition associated with current is through. So if you tell me that the current across some component is so many amps, I will look at you funny and furrow my eyebrows. You want to say the current flowing through some element instead. Okay. So especially voltage and current, those are going to be the quantities that we're going to be dealing with day in and day out. Occasionally we'll find it convenient to deal with charge instead of current, because that lets us work, let's say in some cases, with algebraic equations instead of differential equations, sort of taking the integral of current and getting equations with charge, so they integrate the time variable out, and that makes our life easier in some cases. But for the most part, it's going to be voltage and current. The last quantity that we're going to be talking about here at the beginning is power. Of course, power is denoted by P, and the units of power, the watt, or watts, denoted by W, and 1 watt is a joule per second. So power is a rate of flow of energy, or rate of consumption of energy. And in terms of electrical variables, power is equal to current times voltage. So we can check the units on that. So 1 watt is 1 joule per coulomb. Is that the same as 1 amp times 1 volt? Well, an amp is a coulomb per second, and a volt is a joule per coulomb, and so the coulombs cancel, and we're left with 1 joule per second, and so that checks out. We're not necessarily going to be concerned with computing power consumption in a circuit as a matter of course, but power is a very important specification for many electrical systems. So if you think about your cell phone or mobile computing devices, edge computing devices, everybody is concerned with getting more and more computation out of a certain amount of battery life and certain time between having to recharge the battery, and so that has made power dissipation sort of rise in importance in the last few years to a very, very prominent position in the list of specifications. And so we want to try to minimize power consumption whenever we can, and that is our concern. That's going to be what our main concern is with power. So those are our basic quantities. Now we're going to talk about a sign convention. So sign convention. For I and V. So I guess I forgot to mention that for our purposes we will be using what's called conventional current flow, which is reckoned as the motion of positive charge carriers. Of course, because Ben Franklin didn't know about electrons, we have the unfortunate situation where the actual movement of the charge carriers is in the actual opposite direction to the flow that we reckon as conventional current flow. And so there's going to be some consequences of that that are rather sort of unfortunate, but that's the convention that everybody uses, and so that's what we're going to be following. So if we have some element, some circuit element, which I'll just draw as kind of a blob here with a couple of wires sticking out, and it has some voltage across it and some current flowing through it. Current will flow from the higher potential, the more positive side, to the more negative side. And so the product, if the product is positive, the element is consuming or dissipating power. If so I'll put it up here. If I times V is less than 0, the element is supplying power. So if we adopt this convention and we associate current flowing into the positive terminal and current flowing out of the negative terminal, if we have something like a resistor, we'll find that a positive voltage and a positive current flow, given this association of directions, will result in a positive power computation. If we were to take something like a battery that's hooked up to a resistor, we would find that the current is flowing out of the positive terminal of the battery into the resistor and then back around to the negative terminal of the battery. And so the current in this sign convention would be negative, and so the product of I times V would be negative, and the battery would be supplying power to the resistor, which would be dissipating it. Okay, so we could draw that example here. So if we have, we haven't talked about the symbols of these things, but if we have a battery, which is symbolized by this sort of short line and long line that are in parallel with each other, connected across a resistor, which is denoted by this funny squiggle, there's some, let's say 1.5 volts here. The positive side is denoted by this longer lead, and there would be 1.5 volts across the resistor. The current would flow in this direction out of the positive terminal of the battery and through the resistor and then back to the negative terminal. And so the voltage on the battery would be 1.5, positive 1.5. The current would be negative because it's flowing out of the positive terminal. The power would therefore be negative, and then in the resistor we'd have whatever the same current is times 1.5. Of course, the magnitude of these two things would be equal to each other, but their signs would be opposite. And so that's going to be our sign convention. Current flowing from high potential to low potential for a dissipative element. Okay. So how do these quantities combine together in a circuit? So these are what are called Kirchhoffs laws. Okay, there are two of them. And the first one is Kirchhoffs Voltage Law. Which I will be denoting hereinafter by KVL. Says that if I have some, let's say some circuit elements, doesn't really even matter what they are, and I've got 2 points in the circuit, let's say A and B, or maybe B. Let's put B up here, A down here. It doesn't matter how I go from A to B, the potential between A and B will be the same. Doesn't matter how I get there. So I might have some voltages across these elements like this. I could call this, let's say, V1, V2, V3, V4, and maybe V5, V6. Kirchhoffs voltage law basically tells me that V1 is the same as, I didn't put any signs here, is the same as V6 plus V5. It's the same as V4 plus V3 plus V2. So no matter how we get from A to B, or no matter how, more precisely, no matter how we move a charge, let's say, it takes the same amount of energy. So that would basically tell us V1 is equal to V2 plus V4 plus is equal to V5 plus V6. Okay, we can also express this another way, and that is to say, if we go around a closed loop, so we go back to the same place in the circuit, the sum of the voltage drops, or the voltage rises, is equal to 0. Or we can say that the sum of the voltage rises is equal to the sum of the voltage drops. So we can also say in a closed loop, when the sum of the voltage drops is 0, or 2, the sum of the voltage rises is 0, or 3, the sum of the voltage drops equals the sum of the voltage rises. And these three things all amount to the same statement. So as I go around the loop here, let's say, if I meet a minus sign as I traverse an element, that would be a voltage rise because I'm going up from a negative potential to a more positive potential. If, on the other hand, I meet a plus sign first, that means I'm going to be dropping the voltage. So I'm going from high potential to low potential. And so the sum of the voltage, so in these first two ways of expressing things, a voltage rise would be a negative voltage drop. Okay, so on the first way of doing things, I might write for this loop minus V4, minus V3, minus V2, plus V1 equals 0. So our example for statement 1, we might write minus V4, minus V3, minus V2, plus V1 equals 0 volts. Okay, so we have 3 voltage rises, which are negative drops, and 1 voltage drop, which is positive in this equation. So in the second way of phrasing it for this same loop, we would have basically the sum of the voltage rises, so that would be V2 plus V3 plus V4, so V4 plus V3 plus V2 minus V1 would equal 0 volts, where here in this case, a voltage drop is a negative voltage rise. And so in the second way of writing it, we would have V4 plus V3 plus V2 minus V1 equals 0 volts. And of course, these two are identical equations. It's just a matter of having transposed everything to the other side of the equation. Right? So it's fairly trivial, but these are just different ways of expressing the same idea. The third way, which is the one that I prefer, is the sum of the voltage drops is equal to the sum of the voltage rises. And so you basically add up the voltages that you meet first with a minus sign on one side of the equation, and then you add up the voltages that you meet on the other side of the equation, or with a plus sign first on the other side of the equation. So in this formulation, you'd have basically V4 plus V3 plus V2 is equal to V1. And of course, this is also the same equation where we've just taken all the negative terms and transposed them to the other side and left the positive terms that were there on the other side. So this is the one that I tend to use when I write down Kirchhoffs voltage law equations in circuits myself. Okay. If we were to draw a loop around this whole sort of outer loop and sort of ignore the middle element here, we would have 2 voltage drops and 3 voltage rises. We could also apply Kirchhoffs voltage law around this loop on the right here, and we would have 1 voltage rise and 2 voltage drops, and we would have basically 2 independent equations. Those 3 different Kirchhoffs voltage law equations we could write for this particular arrangement of components have some redundancy. So there are 2 independent equations. The third one would just be gotten by taking the other 2 and adding or subtracting them together. So Kirchhoffs voltage law is really a manifestation of conservation of energy. If we wanted to, we could rigorously derive Kirchhoffs voltage law from Faraday's law, which is one of Maxwell's equations. But maybe what I'll do is, for those of you who are interested in E&M and maybe have seen some E&M before in high school or maybe here at Olin, you might be interested in seeing where KVL comes from, but this is not a course that requires having had E&M, and we're not going to be dealing with very complicated E&M concepts, so we're not going to do that right here in class, but that's the first of our two ways of combining our basic quantities in a circuit. So the second Kirchhoff law we're going to talk about is Kirchhoffs Current Law. And Kirchhoffs Current Law, instead of holding around a loop in the circuit, is denoted by KCL. This is a concept that holds at a node in the circuit, so a junction of elements. So let's suppose we have a number of elements here that come together and let's say there's some current flowing this way, some current flowing this way, some current flowing this way. We'll call this I1, call this I2, call this one I3. And this basically says that the sum of the currents flowing, so this says that the sum into a node is 0 amps. In this formulation, current flowing out of the node is negative current flowing into the node. So we could flip I2 and I3 and put minus I2 and minus I3 and have the currents flowing in, and we would write I1 minus I2 minus I3 equals 0. We could write this also as the sum of the currents flowing out of a node is 0 amps. Right? So current flowing into the node would be a negative current flowing out of the node in this formulation. The third way of doing it, and again this is my preferred way of doing it, is to think about the sum of the currents flowing in is equal to the sum of the currents flowing out. So this is, again, you can write the same equation three different ways by putting either all the terms on the left-hand side or all the terms on the right-hand side, or you can put the terms that are negative on the other side and keep basically some on each side. So for this particular node, call this node A or something like that, KCL at node A would tell us either in the first way of formulating it, basically I1 minus I2 minus I3 equals 0 amps. Second way of formulating it would be currents flowing out, so we have minus I1 plus I2 plus I3 equals 0 amps. Okay, and again, these are the same equation, it's just a matter of transposing everything to the other side and flipping all the signs. And of course, the third way of doing it would be to say, well, the current flowing in is I1, and that's equal to the sum of the currents flowing out, I2 plus I3. And again, this is my preferred way of doing it. And I don't really care which way you pick, which way you like best, which way makes the most sense to you, but you should be consistent. If you're going to pick one way of writing the equations, make sure you are consistent in the conventions that you pick, and it's usually helpful if you're systematic in the way you go about writing the equations that you're going to solve. So for me, it's way 3, where everything is positive and you keep track of the sign by sort of which side of the equation things go on. But that's going to be it for this first segment. If you have questions, you can ask in class or send me an email.